Okay, so today I'm going to teach you about something called the derivative. And now, the derivative is a slightly fancier word for saying the instantaneous rate of change. And now, you probably all know about the rate of change of something. It could be the speed of something, or depending on the situation, velocity, or in simple, just mathematical understanding, the change in something over the change in something else, like with linear equations, delta y over delta x. Now let's say, again, we just have some function here. It doesn't even really matter what the function is. It's just some function that we're uncertain about. And we have 2 points. We have a point, which we will call x, but this is not any x, this is the x. I'm going to denote it without being curved at all, so that we can tell the difference. And we have another point over here. This is x plus delta x. This is a little delta x further. This is delta x, this little space here. Some change in x. Now, so, alright, we know how to take the slope between these 2 points. We know the simple equation. We understand the equation. It's no problem, right? We take the y point of this one, and let's say we know this. This is, right? This is x plus delta x. That's that point. And then we don't know how to evaluate, so f of x plus delta x. Well, this point is x f of x. Right? Now, how do we find the slope between these 2 points? Well, we take the second y and subtract the first. So we take, where's a good place to do this? I'm going to do it here. We take the first y, so f of x plus that little delta x that we are thinking of. We subtract the other y to find the change in y. Subtract f of x, and then divide by the x points. The delta in x points in the same order, or, you know, absolute value signs, but then we couldn't get negative slopes. It wouldn't be accurate. So x plus delta x minus x, we can just take x out, so that's over delta x, right? Alright, so, alright, that's our slope. But what the instantaneous rate of change is, or the instantaneous slope of a function, is the function when that delta x doesn't exist. It's the function, it's the slope at 1 point. Now, how do you get the slope at 1 point? You have no points to compare, it's just a point. So you can't make a line out of 1 point, right? Well, we can use something called a limit that we learned in another one of my videos, and I'm just going to trim off this function a little bit. I need more space. Or I'll just, yeah. Just trim off the graph as well. So, what we can do is find the, put this in brackets, and we find, because delta x can't just be 0, that would be 0 over 0, because that would be f of x minus f of x over 0, and 0 over 0, and that's ambiguous because that can be equal to anything. And that's not satisfying. So we take the limit as our delta x, notice that we're not using x this time, as our delta x gets closer to 0. And this is an arbitrary delta x. It's not like a constant getting to 0. It is just some delta x. This is our instantaneous rate of change. This is indeed what we use to find the slope at a single point. And since there are different slopes, the slope itself is a function of x. So, I'm going to give an example. with a function that we're a bit familiar with. Now, this function, as I like to use, is very simple. It's a simple exponential function because we don't want a linear function. We know how to find the slope of those. Is f of x, curvy x, it's a function of some x, is equal to curvy x squared. It's just normal x. I was just using the other x earlier. And this, of course, continues in both directions. And up again, this is just our first quadrant. Now, let's remember that equation that we made. If we could look up here, I'm just going to rewrite it one more time. We take the limit of this. We don't really need brackets, but we should be level. As delta x goes to 0. And this is how we find our instantaneous rate of change. So let's plug these things in. So, what is f of x plus delta x? Well, x plus delta x is just a point on a graph. And we can simplify all of this before we take the limit. The limit doesn't care. So, this is just our x point. So, this is equal to, we still leave the limit in there because it's still important. We're not just ignoring it. We can't set delta x equal to 0 yet, of, let's see, x plus delta x squared. That's the function it's going through. And as we know, we can simplify that to, oh, wait, no, not that x squared. This is going to become our normal x because this x doesn't matter, just like the other one, but before it was helpful to think of it as a point. So I'm going to just start giving it the curves now. X squared plus 2x delta x, this is just distribution, plus delta x squared minus f of x. F of x, x squared, minus x squared, and then we still divide by delta x. There's nothing to simplify there, right? So, what can we cancel out? I'm going to use my canceling marker. What can we cancel out? X squared minus x squared. 0. So now we have 2x delta x plus delta x over delta x is the same as, I'm just going to write it all out so that it's perfectly clear. Choose a good marker. Okay, this one's good enough. I'm going to change the color here arbitrarily. Can you see this one?
Kind of.
Okay, I'll use another one. Use my blue one. Well, throwing my red one on the floor. Goes to 0. Of these can be separated. 2x plus delta x over delta x plus delta x squared over delta x. I'm going to write it out anyway, just in case there's someone who isn't quite sure what's going on. Now, can we simplify now? No, we're not done yet, because if we simplify now, we still get things over 0. So we need to evaluate this using this same blue marker. So, we come down a little bit. We can cancel these out using our cancellation marker. And we can cancel one of these out, so I'm going to cancel the exponent. The 2 exponents now, it's a 1 exponent. So we get the limit of, it is now 2 curvy x, and always was. Oh, okay, that's a weird x. Never mind. Plus, right? Yeah, this x is too large. No, I'm not comfortable with it. Delta 2x plus delta x squared over delta x is just delta x. Now we can evaluate this. Oh, wait, as delta x goes to 0. So if delta x is 0, what is this? What is our instantaneous rate of change? Well, this right here is 0. So all we have left is 2x. So this is the, draw a line out here, instantaneous rate of change, or the derivative. Alright, so that means